Hey everybody, how you doing today? We're going to get started right here. And we have a few questions. How would you suggest studying for the midterm for 320? I've been working over the assignments and rewatching lectures. Do you have any suggestions? Great question right there. So I'm going to address that right now. Let's hop over to a notepad. Let's do it. Let's hop to the notepad right here. And so for the midterm in 320, we'll talk about this, then we'll hop into, I think Parker asked a question, then we'll go to Nikki's question. So let's do this right here. For the midterm in 320, midterm 320, midterm BAS, midterm 320. So what you have to start here is coding. And so the coding is going to be mainly the take home. So I would not really, there's no real good way to study for coding. You can't be like, tonight, I'm going to become a great coder. Coding's going to take time. It's going to take data camp. So just keep practicing coding. When you get stuck, ask for help. Hopefully people in the chat can say, like, when you're stuck, ask for help. Ask for people to explain things. Hop on the Discord, meet with people, ask me questions. I was just meeting with a student before this, and you just have to ask questions. The more questions you ask, the more you learn, the more you figure out your errors. And we do all have Google right now, but sometimes you just get stuck. And so ask questions. So with the coding, the take home, practice coding, data camp, and ask questions. Brian Discord. So that's how I would get good at the coding, which is part of the midterm. Now we do have some chapters coming up right here. And when you think about this, it really comes down to knowledge. The best way to do this is know your output. If you can explain basically all the output, you know all the concepts. So when you think about the output right here, we've got, let's look at some basic output right here. So the basic output we have is going to be things like this right here. You need to know how to read the associate function. And anytime you get output right here, you need to be able to read through it. Here's your check mark. If you know what everything means in the output, if you know that this is a scatter plot, if you know this is a scatter plot, which is a bivariate display of data, if you know these are histograms, which are univariate displays of data, if you know right here you're looking at shape, shape, center spread, strength, direction, form, unusual features, if you know this is the permutation procedure down here, you're good. Every one of these things in the output, along with the numeric output, which is what we were doing today, should make sense. Whatever prints to the screen here is basically the concepts we've been covering for each chapter. So here's a real quick question, Alexandria. Let's see, 100-point questions. You ready? What should we use here, Spearman or Pearson? Spearman or Pearson? What should we use for this graphic? Spearman or Pearson? What should be used for this graphic, Pearson or Spearman? And so when you look at it, I see something going on right here. I see some stuff down here. So what should be used? What should be used is Spearman, because this is non-linear. So questions like that, when we look at the output, is very important. So if I'm studying for the test, I'm going to go back and rewatch the lectures. So rewatch lectures, understand how concepts connect to output. Kind of, and maybe I'll post some videos. I should have time to make videos, I hope. Everything's so quick. But maybe I can make some videos going over the output for like each associate function. I think that would really help. Rewatch is not apparently a word. But if you're looking for the big things to do, rewatching the lectures, going over the output, understanding what you're looking at and why it matters. So connecting the concepts to the output. So very, very important. You should know instantaneously. There's my mixer. You should know instantaneously that this right here is the permutation procedure down there. So you should know that that is the permutation procedure. Very, very, very important. So let's hop to the first question right here. Can we go over, you know what, let's do, so Nikki had written an email before, so we're gonna go to Nikki's question because she emailed first. Sorry, we're doing everything in reverse order. Nikki, let's go and do a little Canvas content quiz review right here. And so I need to bring up the Canvas content. I'm gonna do similar questions to the Canvas content right now. I can't speak. So let me go do similar questions to the Canvas content. And I'll have that up here in just a second. How is everyone doing today? How is everyone doing? I think we're streaming, right? We look to be streaming. Always my fear that we go like the whole hour and then I look and it didn't stream. We had one day when the internet literally went out, or the YouTube went out. The YouTube. It was a random crash, and it was just like we were streaming, and everything went crazy, and it crashed. Okay, let's do 2 of these questions right here. These are in the Kahoot. So, oh, it's a really good question right here. So let's look. Perfectly, it relates to this. So this is 320 201 questions. 201/320 questions. Okay. Okay. So 201 320, if you're here right now, this relates a lot to your Kahoot, or relates a lot to your so many assignments today. I know there's so much going on. Because it's good to see you, Parker and Nikki, right here. And so this is questions related to the Canvas content. It also applies to 320. So what do we see right here? This is the what for the correlation. So when you look at the correlation right here, the correlation has a what value. Who knows in the chat? 100 points. Correlation has a what. And then what do we care about this value? We should instantaneously look at the correlation. This is a somewhat strong positive linear correlate, a little nonlinear at the end with outliers. So we've got this correlation right here. And then the correlation has a what right here. So the correlation has a what? What does the correlation have? The correlation has a what value? The correlation has with it a p-value. This relates to chapter 6. This is correlation. So this is questions related to correlation right here. So every correlation, and we also see this in jump output, if we do a correlation over here too, and I'll show you the jump output version of it. So we could do the roller coasters right here, and we could make this similar output here in jump where we go to multivariate, and we look at these 2 variables right here, and we see if they see there's a little bit nonlinear, there's outliers here, but we have a correlation of 0.845. This is a correlation matrix where the speed and the height, does this make sense how we're looking at the correlation between speed and height? We can go a little bit more complex on this and do a correlation matrix with all these values, and now you get this correlation matrix. So you could look at the correlation between different things right here, and here's a really quick question that's like the Canvas content question. What is the strongest correlation here? Between what and what is the strongest correlation? Between what and what is the strongest correlation? Which kind of makes sense when you think about it. These are roller coasters. So what has the strongest correlation right here? What's the strongest correlation right here? And this is all about correlation right here. The values between what and what have the strongest correlation. Speed and drop, bingo. And the closer, and if this was negative, it wouldn't matter. It'd still be just as strong if it was negative. So the speed and the drop, and we could look over here. This is actually symmetric. If you were to fold it over, it would be the same values on either side. So speed and drop have the strongest correlation, and the correlation's closer to -1 or 1 is stronger. So what we can do is we can go to pairwise correlations. Where's my pairwise? And this gives us all the p-values. I'll move it over here to the side. So these p-values you're seeing right here, this p-value, this p-value, this p-value, this p-value, this p-value, this p-value, is the same thing we're seeing right here as this p-value. The p-value tells us if our correlation is likely or unlikely by random chance. So think about the p-value like winning the lottery. If this was your odds of winning the lottery, would you say it's likely you're going to win the lottery or unlikely you're going to win the lottery? If the p-value is kind of like the odds of you winning the lottery. So the p-value right here is the odds of you winning the lottery. You'd tell me it's what that you're winning the lottery. Unlikely, exactly, because it's a low probability. So the p-value is the probability of our results being by random chance. I'm going to just say it that way for the moment. But would you say our results are likely by random chance or unlikely by random chance? Since now I'm saying the p-value is the probability of our results being by random chance, and don't this is not a trick question, not a trick question. You would say that our results were what by random chance? Our results were what by random chance? So it's not a trick question, I promise. I'm not trying to trick and change it. So if we look at the p-value as what it actually is, the probability of our results being by random chance, then this would tell us unlikely. Yeah, no, it's not a trick. It's not a trick. Great job, Nikki, right there, 100 points. It's the same thing. And what are we looking at right here is if you have points and you have a correlation, a high p-value, so a high p-value, which would be something like, let's just say a p-value equal to 0.784. That's a very high p-value. Or a low p-value is something like, p-value equal to 0.02. That's low enough. Let me zoom out just a tiny bit. So that p-value there is low enough. And a low p-value is going to look like something that's unlikely due to random chance. This one, I don't know. Statistician's going to come on here and say that should be even lower. Yes, it should be. It should be like 0.00001. This one would be very, very, very unlikely due to random chance. So it's going to have an even lower p-value because it's even less likely due to random chance. And this one right here should look like it's due to random chance. And what do I mean by that? I mean any sort of relationship between x and y, the x variable and the y variable, would just be due to random chance right here. And if you look at it, if you were to draw around it, it has a correlation close to 0, and this one has one closer to 1, if you do the trick of doing the ellipse around it. So we can see that stronger correlations are generally more significant. And what does more significant mean? Lower p-value. When is a p-value statistically significant? When it's less than 0.05. So p-value less than 0.05 equals statistically significant. So very important that we have this is statistically significant. So a p-value less than 0.05 is statistically significant. Very, very important stuff right there. So this relates a lot to the Canvas content quiz. In chapter 6.78, that's pretty strong. It's the wording of strong or weak or moderate. It's so subjective that a lot of statisticians refuse to use it. Pretty much think of it this way. Here, I'll draw something out right here. If you were to, here's what I would say. So absolute value doesn't matter, like if it's 1 or -1. So 1 is perfect. 0.7 is strong. 0.25 is weak. 0. So this is not, these don't have to be called this. It's all subjective. A strong line, and then in 7 is opposite. You might have to explain more, Nikki. You might have to go into greater detail. Perfect correlation must look like the following. Perfect correlation must look like the following. Perfect correlation would be every point is on the line. Non-existent correlation has 2 possible examples. It'll always have the flat line because we're talking linear relationships, but it could be complete randomness, or it could be a relationship that is simply not linear. So you can get non-existent right there. But chapter 7 opposite, I'm trying to figure out what okay. Yeah, feel free to ask questions about chapter 7. Chapter 7's it's basically an extension of correlation. And moderate right here is going to look something, it doesn't matter the slope of the line. You can make a line like that. Slope does not matter. It matters how spread out the points are. So it doesn't matter if the line is less sloped here. It just matters how tight the points are around it. So I'm putting the points tighter around it. So by putting the points tighter around it, we make a stronger correlation. And I feel like I put them a little too wide there at the start. There we go, that's better. And then this is going to be the weaker correlation right here, which you can still have a line that goes up. The points are just going to be a lot more spread out around it. Yeah, sure. I'm trying to see if it actually would fit the line through that. I'm like, okay, well, that actually... So what matters with the strength is the vertical scatter. Does this make sense to everybody right here with what I've drawn? That the vertical scatter is what matters. The vertical scatter is what matters. So if you want a strong negative, you could have a strong negative correlation like this, and then the vertical scatter is going to be tight around it. So that's a strong negative. It doesn't matter the slope of the line. The vertical scatter of the dots is what makes something strong, moderate, weak, non-existent. And then this is kind of not really a trick question. It's just not a linear association. So there's no linear correlation right there. So I think we're good on correlation, understanding the strength, direction, form, and unusual features. So make sure you can go through those. We've been covering those quite a bit right here. And feel free to ask if you have questions on them. And chapter 7, can we go back? Yeah, let's do it. Let's do it. And I'm trying to see, so we've done that, a p-value, residual. Okay, so it's asking about residuals. And find the predicted value for regression equation where, so with the regression equation, because I think that was something else you wanted to cover. With the regression equation, let's bring up a regression equation here, and let's see how it relates to writing out the equation we do in algebra. The regression equation is as follows. Y hat, which stands for the predicted y, equals to b0 plus b1, and those are subscripts, x. Now, when we do this, it can be certain things like, let's just do a formula right here. So we could have, and we can go to insert, there we go, equation. And I'm doing all of this just to put a hat over it, because I could have drawn it. We could go here to someone's predicted height is equal to, and let's go here to 40 plus 0.3 times weight. Okay, so with this right here, we have an equation, which might turn out horribly, and we are basically putting everything next to where everything belongs. Trying to get it all lined up. Might be the best we're going to do today. If I could highlight all that, I can't. But notice how everything is kind of in line with where it's at. You know what we can do? Watch this. Because I want to make this very, very clear what's with what. The predicted height is y hat. This is the intercept. This is the coefficient of the slope. And this is the x variable. So when you visualize this, here's where this visualizes out to. We would have here a line. The line would hit here at 40 on the x-axis. So the 40 that the line hits at when x is equal to 0, or the y-axis, excuse me, this 40 right here is b0, and that's when x is equal to 0. So if you think about plugging in an x of 0, think about what this would solve out to. With an x of 0, this would go away, and you would just have the coefficient right here. So we'd lose off this right here in the equation, and it would just solve out to 40 because you plug in an x of 0. So we'd say when someone has a weight of 0, we'd expect their height to be 40 inches on average. Now here's the thing though, that doesn't make sense. You can't have a weight of 0, and if you did have a weight of 0, then you wouldn't have a height. So always think about the interpretation, like say it out loud. When somebody's weight is equal to 0, we expect their height to be 40 inches. Doesn't make sense. So it's a logical intercept. The other value we have right here is the slope, and the slope is 0.3, which means for every 1 unit increase in x, so if we go 1 unit up in x, we'd go 0.3 up in y. So this little distance right here, I guess I could draw it bigger. If this is a 1 unit increase in x, then this would be a 0.3 unit increase in y. So to make this more accurate, my line needs to be a little less sloped. It needs to be like a third of a unit up like that, so it needs to go like that. So a 1 unit increase in x would be a third of the unit increase in y. And this right here, this difference that y is going up is 0.3. So every time x goes up by 1, y is going up by 0.3. And that's what this stands for right here. It's that increase in y for every 1 unit increase in x. And a good way to remember this is for each 1 unit increase in x, because it's b1, we expect y to increase by, and then b1. So make sure you have these interpretations. I've got them in a lot of the notes, but for each 1 unit increase in x, we expect y to increase by b1 on average. Now be careful, it could be decrease. I do say increase, but if this is negative, you do need to say for each 1 unit increase in x, we expect y to decrease by b1 on average. So, and on average, you can't say if you want. I don't know, sometimes I say it. It shouldn't be required. It should not be required. I'm not for on average because we're saying expect. And the x value here is just the x variable we're using. So another big equation we need to know. So we need to know what to solve for this. Try thinking about this and solving for your own height. Oh, it turns out horrible. If I put in like 200 pounds, I'm not 200 pounds, but if I put in 200 pounds, it says I'm going to be 100 inches tall. So in truth, sure, this equation works out crazy. Like, so right here, you need to know that B0 is this, B1 is this, and be able to write the equation out with y hat equals B0 plus B1x. And if you're wondering how this relates to algebra, this is y equals mx plus b. So this is y equals mx plus b. It's just the way we write it in statistics. You can, just knowing the notation is key right here, and understanding that b0 is the slope. It's when x is equal to 0, and b1 is the oh my gosh, b0 is the intercept. It's when x is equal to 0, and b1 is the slope, and it's for each 1 unit increase in x. So the other big thing to know for the Canvas content quiz is definitely residuals. And so let's go ahead and compute Brian's residual. What would Brian's residual be? And this is good for 320 also. 320, listen up if you're here. What would Brian's residual be with this equation? Brian is actually 75 inches tall. So that would be Brian's y value. So Brian is actually 75 inches tall. So Brian would be down here. Yep, that'd be right. So I'm down here at 75 inches tall. And so Brian is actually 75 inches tall. How would I get the equation of the regression with mean and standard deviation? Do you have the regression solver? That is key. I'll show that off here. The regression solver is key. This should be loaded up on Canvas for you right here. So on Canvas, you should have the regression solver, and you can just plug in the numbers. The formulas are in the notes. They're not fun to do, but the regression solver should be on Canvas. Does this make sense, Matthew? So if on many questions, it'll give you these numbers. And so Tiny Brian made this. He'll tell us.
I'm Tiny Brian. I made this.
He can go away now. So this right here is the regression solver. I have nonsense numbers in it, but you'll put in here the correlation. And so that's just the value of R. You'll put in here the standard deviation of the Y variable, whatever that is. You'll put in here a standard deviation of the X variable, whatever that is. You'll put in the mean of this variable. You'll put in the mean of this variable, and it'll give you the equation here for the intercept and for the slope, which kind of reviews the notation. Oh, no worries. Glad you found it, Matthew. Excellent job there. Yeah, this makes it way easier. We're not here to solve math problems. We're here to interpret stuff and to figure out the answers. And so this makes it way easier because, I mean, if you're going to plug into a calculator, why not design this? So I designed this, and you can also put in the numbers here, and it'll solve out for you on this. So if you put in the numbers here, it'll solve the regression equation here. So, and you can see how it's kind of doing the means and the standard deviations and the slope. And you can see it kind of made the line. I should have made something that graphs it also. So I don't know, maybe I'll go back and make Regression Solver Pro 3.0. So, but yeah, where in Canvas is the regression solver? It should be under modules. It should be under modules. Here, I'll show where it's at. It should be under modules. And I know our class has the updated one. Please email me if you don't have the updated one. Regression Solver Pro is right here under the section we're doing. So that's where it's at. And if you have any questions, feel free to ask at any time, anytime. We're here to help everybody. So, you know, ask away. Here's the Regression Solver Regression Solver Pro. And you have to know a little bit about how to use it. If you have questions, feel free to ask. I used it. I could do a problem here soon. We're going to do a 474 problem, I think, in a moment. More questions if you have them. I'm going to mention how to do a residual here. Who here can predict Brian? If Brian weighs 200 pounds, what is Brian's residual? So what do you need to find Brian's residual? Because we've got an equation up top right here to figure out Brian's predicted height. So if we want a residual, we have to remember what a residual is. A residual is going to be the formula. Residuals are equal to actual minus predicted. So we'd have to get a predicted from this line, which would be the prediction for Brian. That's a little y hat right there. So we'd have to get Brian's predicted height, and Brian's actual height. Now we know Brian's actually 75 inches tall, but we need a prediction for Brian's height. In notation, this is E equals to Y, which is the actual minus the Y hat, which is the predicted. So we already know Brian's actual height is 75. Plug that right there. And then we just need the predicted. So what we're going to do is we're going to go to this formula and we're just going to plug in to this formula the numbers. We're going to go 40 plus 0.3 times 200 to make the math easy. And that should give us 100. This formula is ridiculous. So now we have 100 is the predicted value. So we predicted Brian would be 100 inches tall, like one of the tallest people ever. And Brian's actually 75 inches tall, so his residual is negative 25. So that's how we solve for the residual, and the residual is this distance that I am away from my prediction. So when you look at this, the further I am away, if I am 75 inches tall, then that's how tall I actually am. So this would be y equal to 75 inches, and then this up here is the prediction. This is y hat equal to 100, and then this distance right here with rainbow pen is going to be the residual E of negative 25, which means this prediction for Brian was 25 below, or Brian was 25 below his prediction. Does that make sense how we're solving the residual right here? Brian is 25 below his prediction. So the residual is the basically how much we miss by. It's the vertical distance we are away. If something has a negative residual, then the actual was below the line. If something has a positive residual, then the actual was above the line. So you can think of this as the positive residual zone, down here as the negative residual zone, and right here, anything on the line would have a residual of 0. Because if it's directly on it, there's no miss from its actual and its predicted. I think that's good. Did that help out, Nikki? Did that help out going over it? I think we're caught up on all the questions. Great questions today. So I think that shows how to do and understand what a residual is. And hopefully that's got it. We're going to hop over here because I think Parker had a question or two on 474. If you have questions, feel free to ask. If you have questions, let me know. Let's go grab that 474. It is Haslam Friday. You know, I wish I had a day that was called like Brian Friday. It's Brian Friday. See, we should always have Haslam Friday. I miss seeing the employers in Haslam. I saw some people I saw on LinkedIn that they were doing it, but I miss like Eastman would bring like donuts. I should not talk about the before times. I shouldn't do that. And I'd be like, oh, I don't want to take a donut. They'd be like, take a donut. They'd be like, we have so many donuts. You need to take a donut. And I'd be like, okay, I'll take a donut. I will take a donut if you insist. You insist, I shall take a donut. Let's do this right here. Parker, if you're here, we're going to do a little 474 part. You had questions on questions 1 and 2. Let's take a look here. Questions 1 and 2. So let's go here and do that. Okay. So we want to look at question 1. Write a function named compute that takes 2 arguments. Okay, so the function should return the vector blah, 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 blah. Build a warning message that says the Q argument is intended to be a single number if the user passes Q as a vector or 2 or more. So let's kind of do this in parts right here. Let's do this in parts on this first one. I might just do this first one right here. But so we want to return this. Okay, so doing this in parts right here. I made a mistake on it. So the function takes 2 arguments. And so I'm going to do this in parts. I would not suggest, let me do this. Don't do what Brian is doing. He is doing this in parts. So remember, we always code in, everyone knows, code in little bits here. We don't always code the whole thing. We want to make sure we get the parts done. And right now we want to basically use this function. It's built for us. We can just test it out right here. That's a graphics error. We can test out this function to see if it works by going right here and running it, and it works. So just put it in a function. Let's go here and go fun for fun, because F is friend, the two stuff together, U is for you and me, and is for anywhere and anytime at all, down here in the deep blue sea. And let's go here and type Z, comma Q, and we're going to call this compute. And we're going to run the function. And there we go. We've created a function called compute that takes z and q, and we need to put a return on this. And we're going to return this value. It would return it anyways, but we should put a return on it because it'll return the last thing, I believe, but return is how you end a function. So the reason you put return is you're like, stop here, return this, function over, we're done. So we're going to go here and run compute, and we're going to check we get the same value. That's the value we got just a moment ago, and we can probably remove everything from our global environment and make sure it works now. Let's remove this. That was some kind of work we did, and it works. So we've now made it that the function works, but now we need to build a warning message. So a warning message starts with warning, and there's 3 levels of messages. There is just a message, there's a warning, and there's a stop. And I think we still have the notes from today up, the notes we took. Was it here? No, it wasn't there. Did I delete it? Don't tell me I deleted it. No. I'd be so sad if I deleted it. It's going to be Untitled 3, right? Be Untitled 3. No. Did we? Okay, it wasn't that one. Well, don't tell me I deleted it. Why would I delete that? Oh, there we go. Well, it's gone. It's gone, it's gone. So we had some notes up earlier showing it. I don't know why I would have deleted it, but we had some notes up showing the differences between a message, a warning, and a stop. A message is just going to show a message on the screen. A warning is going to still run your code, but show a warning in red. And a stop is going to completely stop your function. Stop. Game over. Done. So this is just a warning right here, but it says the argument is intended to be a single number if user passes q as a vector of 2 or more numbers. So what do we need to do? We need to look at q. So we need to go here and look at q, and we could store a q in the environment to just look at it. There's a q. And we want to look at the length of q. Length of q is 1. But what if q were to be something like this? This is when we want our function to stop if q is larger than 1. So let's look at the length of q here. It's 2. So what about if we look at length of q greater than 1 and we run this and we get true? So now we want some code to run here. So let's go ahead and put this in an if and put a warning. And it'll run this code now for the warning because the warning will print. And we'll drop this right here. So if you notice, we kind of got the condition working, and then we're just going to take the condition and drop it into here. And now we're going to test it out by purposely trying to break it or make our message appear. We'll put the vector in here of 2, 3, and we'll run it, and we get the warning message. The Q argument is intended to be a single number. So if you notice right now, we do get our warning message of telling us, hey, you shouldn't be doing this. And we just did a condition to check to see if the length of Q was greater than 1 to see if it had more than one thing in it. So the syntax of warning, all that good stuff right there. Once your function is written, uncomment the 3 grid lines so their output is knitted into the document. Oh, cool. So is that it? So this right here computes, and then we get our warning message. So that should be it, right? Your custom warning should output as well as 2 numbers. And so this right here computes more numbers. I think everything's right because it's doing that function. And Q is meant to be 1 number. So it does print the warning message. Is that all of number 1? Well, darn. I was going to do part of it, and then we ended up doing all of it. So the biggest thing right now is coding in these little bits to make sure you get it. And always start out coding small, code outside of it. Make sure you get it correct. And what was it, question 2? And ask questions if you have it. We've got 25 minutes left, so we're good on time. I'll do part of question 2 already. Let's look at question 2 just a little bit. Cumulative sum. So when you look at a cumulative sum, what could we do other than cumulative sum? Cumulative sum is going to be when you add up all the elements. When you think about numbers in a vector, the cumulative sum of a vector is going to be each element's sum added onto each other. So the cumulative sum of this would be 1, 2, 3, 4. The cumulative sum of this would be -1, 0, 2, 5. And it's probably a function already written in R that does it. But when you think about this, it tells you how to do it right here. In other words, for the return value, its first element is the first element of the vector. The second one is the sum of the first two elements. And so you can probably do this with a for loop. All right, this with a for loop right here. Can we go over some more? Yeah, let's do that. Which ones do you want from chapter 7? We've done a few of them. We could do chapter 8 too if you want. Is there one you're stuck on right now, Nikki? So with this right here, you do want to write a for loop. And for the for loop, you want to go and let's take a vector x. And vector x is going to be these, sure, why not? These numbers right here are going to be vector x. And we want to go in here and we want to store into csum. So cumulative sum right here, we want to store into it in position 1, whatever is in 1 through 1. And some of it. Well, this is basically got it. This is the start of it. That's the harder part. Oh, because I didn't create it. Sure. There we go. And so that's basically your skeleton. So I might leave this one with this right here because that's your skeleton. And now you're just going to go through and start storing things through here. So I hope, Parker, this really helps a lot here because that's your skeleton, because I can now work with this. I'll show a tiny bit more. I can now work with this to create the following and then check my work after each one, and we can get the cumulative sum like this. Of course, I need to stop at a certain point, but yeah, does this make sense, Parker, where we're at here with this? That this is the skeleton, and then knowing where to go from here with the skeleton. Oh, no worries, no worries. Here, pull it up right now and ask one of the ones you're working on. We'll work on that one. We could work the ACT one again. A lot of people have problems with that one. That one's a pretty tough one that people usually get stuck on. Probably a good one to put in the video again. No, the SAT one I meant to say. The SAT one's the trickier one people usually have problems with. That one's pretty tricky for most people. But yeah, so I just made the cumulative sum right here. I didn't do it as a for loop. And then once you create the for loop, you can just put it into a function and change what the vector x is. So this is 50-60% of the work on this one, just creating this right here. And that's the skeleton. And I've already identified what the vector is. And the vector won't be 1 through 6. The vector will be, this one's 1 through 4, and this one's 1 through 4. This one is now 1 through 7. Not because of that. It's now 1 through 8. Now it's 1 through 9. Now it's 1 through 10. So I would have to control it via the length of the x vector to make sure it augments to that. So let's hop here to some 201 homework. Excellent work on this right here. 201 homework. I think I've got my Pearson up. My Pearson. We'll do some 201. Homework 7. Here we go. We're almost to the SAT question. Okay, let's look at the SAT question right here. Did I do the whole quiz? No, I did the whole quiz for 6. That one's fun. Here it is. Okay. So this is one of the problems that gets people really, really stuck. This one right here has a lot of big concepts. Oh, you're welcome, Julia. Thank you. That's what I came here for. Hoping you'd go over. Yeah, sure. Oh, was it yeah, good. This one gets people stuck. That's what, and feel free to ask questions. I having taught this class for a decade. I'm getting old. I usually know where people get stuck on problems. So this one right here asks, we have math scores being predicted and we have verbal scores. Oh, look, that person made like a 250 on their verbal and an 800 on their math. Does anyone have an estimate of what their residual would be? Who knows for 1,000 points? Quick 1,000 points out here. Who can estimate what the residual of this person would be? They made an 800 on their math. And 250, 800. Who knows what the residual of this person might be? Because the residual is this distance. They're the biggest residual in this plot. They're the biggest outlier / they have the biggest residual, which means, in magnitude, because this person's a pretty negative residual. This is the negative residual zone. These people have residual close to 0 because they're basically where the line is. The line is all the predictions, and then the people are the actuals. We were graphing this out earlier right here, where you can see the line has all the predictions on it, and the residuals here are positive above the line. Things on the line have 0 residual, and things below the line are negative. Like right now, I have a negative 25 residual from earlier when we did this question. So this person right here probably has a residual close to 450. How do I know that? This is 800, and maybe if you trace this over, that's about 350. I don't know exactly where that's at. Maybe that's 300. It's hard to say. They probably have somewhere between like residual of 500 to 400. So they're very large in their residual. It's just that distance right there. So what would we say right here? Well, it's positive, so that's true. And the people with higher math scores generally have higher verbal scores. So there we go, because it's a positive relationship. So if one goes up, the other generally goes up. Doesn't have to, but generally speaking. Are the students whose scores do not fit the pattern? Boom, right there. That's a person with a verbal score of 250 or so and a math score. So we just see the 250, and that is the answer. And next, I'm going to use the enter trick. Oh, it's not working today. And so for the data, the correlation is this. Now, this is where we need to pause, because with correlation, we can get R squared. And R squared, let's review. R squared is blank percent. So R squared is equal to blank percent of the variation in Y is explained by the variation in X. So blank percent of the variation in Y is explained by the variation in X. So when you think about this, we need to put in the values of Y and X right here. So let's see our graph again and make sure we get it. We first need to compute R squared. R squared for this, let's compute it, is not that. It's going to be 0.359 times that. It's about 29%. So do we see 29% in here? Oh, it's behind my head. Where'd I go?
Tiny Brian. Okay. So 29.1%, that's the right answer. So we have to look right here. For one standard deviation.
Students who scored one standard deviation above the mean and verbal are expected to score above. So right here, students who scored above are expected to score above. This shows us a positive relationship. So with the positive relationship right here, that is indicating the positive slope. This other one down here that also has the correct R squared indicates a negative relationship. So if you see right here, it says students who score one standard deviation above the mean in verbal are expected to score below in math. That would indicate a negative relationship. So that's not the right answer. The right answer is going to be this one. We also have 29.1% of the variability in math scores explained by the variability in verbal score, which is very close to what we just wrote a moment ago. 29.1% of the variation in the verbal scores is explained by the variation in the math scores. So very key, we see that my interpretation that I use all the time is very similar to what my Pearson wants you to do. And we did it. We got that one right. Going on to the next question right here. This is where people usually get stuck. This is where people are like, well, don't know how to solve these. And with these right here, I need to once again hop over to here. So with these, the verbal scores had an average of this. Now, verbal is the Y variable. How do I know that? Oh, it's the X. Haha. Verbal is the X variable right here. Verbal is the X. Make sure you know that. Verbal is the X. So we need to go over to the regression solver. The regression solver, make sure you put your numbers into it. So put your numbers into it. We won't use this one. So when you use the regression solver, which can be found right here, here's where the regression solver is under chapter 7 under modules. You want to go to the regression solver. You want to enter in, we're going to look at the mean of verbal, which is the X variable. Let's double check. Make sure it's the X. Verbal's the X. And then we go back here. I'm just going to click this back and forth so I can see it. The mean of verbal, which is X, is 519.8, 519.8. Don't make an error. And then the standard deviation, 169.2. Standard deviation of verbal, 169.2. And then the math score had an average of 544.2. That was the Y variable. And has standard deviation of 164.6. And then the standard deviation, or excuse me, the correlation is 0.539. They kind of try to trick you because they put that in the previous question. There we go. Now we have this value right here, and we'll put it right there. We'll delete the decimals, we'll round it, And we have this value right here, 3 decimals again. We'll put this value here, we'll round it, and we'll check our answer, and we got it. Woo! Give me a heart attack every time I'm doing that question. So easy to make mistakes. Good job, Tiny Brian. So it's very easy to just make an error, put things in the wrong way, but just make sure you put in the right standard deviations, the right means, and just make sure to enter things in the correct way. And then you have the intercept and you have the slope. And then we can also solve, and I'll show how this is solving. But it now asks us, I think, to solve, right? So it asks for the interpretation, but the interpretation of the slope, you should be able to say, if we had you writing things out, I'd have everyone shine this in class if I was in person. So the slope for each 1 unit increase in x, we expect y to increase / decrease by b1. Let's do intercept too while we're at it. Intercept when x is equal to 0, we expect is a keyword, don't say it will. We expect y to equal b0. Okay, so let's go here. Boom. Go here. Put the period. Go to subscript. And go here. And we're doing not putting periods on our stuff. So when we interpret the slope, there we go. When we interpret the slope, we need to put in the words in context, like your Canvas content quiz or like your visualization assignment. For each 1 unit increase in x, so for each 1 unit increase in x, so what would that be? Let's up over here to the assignment. For each point someone has on their verbal score, we would expect their math score to increase by 0.524 on average, because that's where the x is. For each 1 point increase on someone's verbal score, we expect someone's math score to increase by 0.524. So interpret the slope right here of the line. For each unit increase in someone's verbal score, so there's the verbal, we'd expect the math to increase. So verbal score, increasing math, I think we got it, good. Now the intercept, it doesn't ask for, but the intercept would be when someone has a verbal score of 0, which you can't actually have. You can't get a SAT score of 0, you can only get as low as 200. But when someone has a verbal score of 0, we would expect their math score to be 274.1645. So the intercept is illogical for this problem. And make sure to know your interpretations, put them on flashcards, and understand how to use them. Very important right there. The student, we are going to make a prediction right now. The student made a 444 on their verbal portion. So what we do is we take this equation right here. We take this equation, and with this equation, we're going to bring it over to Word. We're going to drop it in here into Word, and then we're simply going to put right here, draw into it. We're just going to put 4, 4, 4, and we're going to solve it. This will predict their, predict their math score. So we go 444 times 0.524 plus 271.645. So the 444 is their actual verbal score, and then this is their predicted math score. So we now have obtained this person's predicted math score. So we would predict, and it rounds to the nearest number, that they would get a math score of the following. Now this is the question that stumps everybody. And sometimes we put a question like this on the test. Everyone's going to freak out. But this question is all about notation. The way to solve this question is to know every bit in the notation. It says every year a student gets a perfect 1600. So if a person gets a perfect 1600, what does that mean? Well, that means they got an 800 verbal, 800 math. So let's hop back here to Word and solve this question. So we've got a few things here to help us out. Not that. What we can do to help out right here is we can write the following. We can write down what x is. If they made a perfect 1600, what would x be? X would be 800 because that's what they made. They made a perfect verbal, which is x. If they made a perfect 1600, then their y would be also 800. it wants to know their residual. Now, residual is the formula actual minus predicted. So E is equal to the actual minus the predicted. If you notice, we're just one step away from finding that. I hope this makes sense right here, because with everything we have written, what should we do? Because if we know the actual, we know this value right here is 800. And I hope this makes this way easier, because we're one step away from solving this now. What should we do to solve this now? Because we're one step away. We know they actually made an 800. What can we do to solve? Because we just want to solve for the residual. We are so close. Does anyone know? 1,000 points out there. How would we solve for the residual? We got 8 minutes. There'll be 8 minutes of silence. People watching the stream later are like, wait a minute. Is it over? Is it done? Does he never get the answer? I'm pausing here I want people to think, what would we do? Because all we need to do is solve for E. And then to solve for E, we need something else. To solve for E, we need Y hat. And to solve for Y hat, because we're trying to get E, the answer is E, but we don't have Y hat. But wait a minute. Y hat is this equation. But for this equation, we need X, and X is this. So why not take X and just plug it in here so that this is 800. And then this is going to solve for the predicted value of the person's math score. So what would we predict their math score to be? There. And then we add the intercept to it. And that's their predicted math score. So we know now that this person had a predicted math score of 690.845. And we can solve the residual. Should be 109.155. 109.155. Let's see, I'm trying to do it in my head. 109.155. Did I do it right in my head? Did it. Got it. Good. So that's got it right there. That is a pretty tricky problem. And the last part of it right there was just solving the math equation right here. I'm doing less mental math. And I'm like, oh no. So that's that right there. So hopefully that makes sense. What we're doing, we're just solving for the regression equation and using basically the line. So when you think about it, this person, if we were to plot them, they actually made an 1800 and they're supposed to make a 690. They made an 800, excuse me, on their score. So if we go back up to the plot right here and we zoom in on it, they would be, oh, they are right there. There they are. They made the perfect, yeah, that's them. So visualizing what we just did, we're going to visualize it here. To visualize the relationship we just did would be to go after all of this. Awesome. And let's put this right here. We can zoom in. Really? Wow. Wow. There we go. That's way too small. There we go. So we have right here that this individual right there made a perfect 1600, which is 800 800. They made an 800 800, and then their residual is this because they were predicted to make a 690.845, and they actually made, so that's their predicted. That is what the line predicts. Y hat is the predictions of the line. Every one of those on the line is a Y hat. And so this is equal to their Y hat. And then their actual, so Y equals 800. And that makes the residual E equal to 1, excuse me. So that makes the residual E equal to 109.155. 0.155. And that's just literally this distance right here. So the distance right here is their residual. So it's just how far off we were in our prediction. We were off by about 109, and they were over their prediction. You can see things with negative residuals here, like this one right here has a negative residual, and just kind of identifying this is key. Any other last questions right here? We're in the last few minutes. Might just do the last question right here. We'll do question 5 maybe to end this. And so when we look at this one here, question 5, we have here correlation between the age and price of a car. And just think about this logically though. As a car gets older, its price goes down. So this would actually make a negative correlation. We could view this in Jump really quickly. Let's just copy this to clipboard. Is there any help on a previous view with quiz 7? Yep. We don't know if I did all of quiz 7, but I'm trying to think if there's any. The questions are very, very similar to this. Here's how to put things into Jump if you want to do the questions in Jump rather than using the regression solver. You can go over here to Jump. I'll show you how to put this into Jump. Go to a new data sheet, and very importantly, paste with column names. Paste with column names. And this will put this into Jump right here. And you can go to Analyze, Fit Y by X, and we can put in the age of a car explains the price. And I also have other videos for the quiz too. Email me if you can't find them. I'll make sure to send it. Oh wait, I put them in the wrong spot. Price explains, no, I did put them in the right spot. The age of a car explains the price of a car. And you see there's a negative, somewhat linear relationship. We can fit the line and we get R squared. Now, one thing, be very careful with this because I don't know if this one ever has this problem. You want to get correlation. So let's square root it. They give us 0.894. We're going to square root it and we get 0.946. But here's the thing, negative 0.946, negative 0.946. And why is it negative 0.946? It is negative 0.946 because it's a negative relationship, because there's negative correlation. And when you square root things, yep, exactly, GG, 1,000 points. Great job right there. It's going down, so the slope of the line is negative. So don't forget that. Don't forget that it's negative. Explain the meaning of the R squared. It would be that 89.4% of the variation in price is explained by age. So age accounts for 89.4% of the variation. I'm not going to get the last one wrong. It's the bane of my existence. Why doesn't this model explain 100% of the variation? It doesn't explain 100% of the variation because real world data could be perfect. That's possible. There's not enough data. Doesn't matter that there's not enough data. This is true. I went into this last time I talked about it, but the answer is going to be this one. Because I just did this question yesterday and I got it right, luckily. But hopefully this helps everyone out right here and people, wrong Brian. Hopefully everyone can understand what's going on and how to analyze this data. And I can probably help out with other things. If you have questions, let me know. Email me if you're stuck on any of the questions. We'll have class here soon, but hopefully everyone feels pretty on track. How's the assignment looking, Gigi and Julia and Nikki, if you're still here? Because we did a lot today. We did correlation, we did functions, we did so much. Good, awesome. Yeah, email me if you have any questions. If you're stuck on any of them, let me know. Might need to put out more videos or do things like that. But the videos are helping, good. It's just practice, it's just review, and then just always try to ask questions and everything. Great job, Gigi. And I'm gonna try to put out some review videos this weekend for the test. I'm gonna try to put out some speedrun videos. I think that's got it. We're gonna prepare for class, and I'll see everybody later. We'll go with a fun ending. These are, oh, Bobby, that's so awesome, man. Here, do we have any? What do we have? Let's do this. Here, we'll do this. We'll have a fun ending. You ready? Okay, wait. Hey, Jason, wait. Can we keep going here, Jason? Jason, we just need to film for like 4 or 5 hours. We've almost got these new intros ready. We're almost there.
This has been going for like 20 hours. This ends now.